A loudspeaker emits sound toward the open end of a pipe. See, the other end is close. This is one end fixed, right? A standing wave is formed in the pipe. Diagram represents the displacement of the molecules of the air in the pipe at an instant of time. So notice that this is displacement to the right. So these particles are displaced to the right. This is a lot. These are displaced just a little bit. These are not displaced. And then these guys are displaced to the left a little bit. And these are displaced a lot to the left. And again, these will be to the right, not as much, and then this not at all, right? Okay, so let's see. Outline how the standing wave is formed. Ooh. Okay, so I don't know if I think I tried to explain this, right? But remember that this is a fixed end, right? Okay, so the wave that would reflect off of this is going to be inverted, right? Because fixed ends invert waves. Okay, and so the incoming wave, if it's this, the outgoing wave, if this wave were to continue, by the way, it would be like that, right? But what reflects back is, of course, the inversion of this, right? And so if you notice, the inversion of this would cause this trough here to become a peak, and that would coincide with this peak. And so basically what's going on is that the incoming wave interferes constructively with its reflection for that particular frequency, right? It's only one mark, so see if you can get that mark there. Okay, X and Y represent the equilibrium positions of two air molecules in the pipe. The arrow represents the velocity of the molecule at Y. So Y is moving to the left. Okay, let's see. Draw an arrow on the diagram to represent the direction of the motion of the molecule at X. Okay. I was thinking about this too. I'm like, wait, what is this? And so, the question is, of course, if this thing is moving to the left, this guy is going to be on the other side of that. So I don't know, think about that, right? I don't know if there's a better way to explain that. But if something that's displaced to the left is moving to the left, then something that's displaced to the right will be moving the opposite direction, right? Okay, label a position N that is a node of the standing wave. There really are two nodes here. Remember, a node is where it's not moving, okay? But they only label one of them as the node of the standing wave. Okay, so see if you can figure out. Remember, a node is where it's not moving. Okay, antinodes are where it's moving a lot. And then it says the speed of sound is 340 meters per second. The length of the pipe is 0.3 meters. Calculate the frequency of the sound. And this is, here it is. We trained for it. The moment comes, can we do it, right? So you're going to set this whole thing up, right? This is how many quarter wavelengths, right? So the length of the pipe is going to be n lambda over 4, right? So figure out how many quarter wavelengths it is, and then figure out lambda. Lambda equals something, right? It comes out even too, because the pipe is 0.3 meters long, and anyway, it all works out. And then find the frequency of this. The speed is 340 meters per second, so then you're going to use V as F lambda, right? V is 340. Lambda is what you figured out. You're going to figure out the frequency from that. Okay. All right.